We've already seen certain types of what we call matrix transformations. When we think about transformations, and before we address this particular transformation, we might remember or recall the idea of functions. So functions are such that we give this function some input, and then the function operates on that input. Maybe what it does is to keep this simple, it doubles the input and it reports that as the output, y equals f of x. And so every number that you put into this machine gets transformed and converted to different values. So if we put in an x of 3, we'd get a y of 6. If I put in an x of 10, I get a y of 20. And we're transforming this number. The way we might think about that is, if we think about a number line, the value of 3 got transformed into the value 6, and the value of 10 got transferred into a value of 20, got transformed into that value. So we can sort of just think about these as these values got scaled up and manipulated in that way. When we conduct matrix transformations, as we've seen before, what we're doing here is we're taking an input vector x and we're multiplying it by a matrix A. And that matrix is going to change that vector in one or more ways. So if that is x, and I multiply that vector by A, I'm going to get a new vector, and I'm not really sure where that vector is going to lie. It really depends on the matrix itself and the vectors that I give it. But I'm going to get this vector called B, and that's the result of taking A times x. And we can see that a couple of things take place. One is there could be a rotation, and then also when we see that we rotate that vector, we get something that maybe lies along here like this. And so we see that that vector also gets scaled up. So the transformation has a rotation and scaling effects. So these are the effects of vector matrix multiplication. All right, let's now think about how this can pan out. This can pan out in a number of different ways, but we know that A is going to be some matrix, which will be, we'll say that it's, for example, 2 by 3. Now, in order for that product to take place, if I have a 2 by 3 matrix, which is 2 rows and 3 columns, the vector that multiplies it would have to have enough positions to be able to multiply all 3 of these columns that we have here. And therefore, this would have to have 3 components as well. So the x vector, what we're saying is that it's going to have to be 3 rows by 1 column. Okay, so notice here that the number of columns in the matrix A has to match the number of rows in the vector x, and we're going to produce this vector called B. Now, how big is B? Well, the initial claim would be that it's 3 by 1, that basically we get a vector that's in the same dimension, but based on the way this is going to take place, it'll be this value times the first column, this value times the second column, this value times the third column, and then we're going to add those 3 scaled vectors together, and so we're only going to get a vector that has 2 components. So we're basically going to be transforming a 3 by 1 vector, which is in 3 dimensions. We have some vector out here. I don't know, let's just say it's one that is maybe up here somewhere, and there's our vector, and that's x. And then we multiply it by A. We take A times the x vector, and we actually end up with something that is only in 2 dimensions. Now maybe what that represents is maybe that's a projection or a shadow of this vector onto a two-dimensional wall. So that's one application of where we might see having, and this would be called vector B, of where we would see something that's in higher dimensions get smashed into something that's in fewer dimensions. But here's kind of the general lesson, the takeaway here, is that if A is an m by n matrix, so it has m rows, n columns, m could be bigger than n could be bigger than m, or they could be the same size, but in general they don't necessarily have to be the same size. And if x is, in that case, would have to be an n by 1 because the number of rows in x has to be the same as the number of columns in A. And therefore we'll get B, which will be, notice, was the outer dimensions. It was 2 by 1, so this will be an m by 1 vector. Now the way we write this is we often say, okay, we're going to have a function that's going to be called a transformation. So this is the name of the function. The transformation will take some vector that's in Rn. Okay, that just means that it's an n by 1 vector. It's in n dimensions, and it will get mapped to a new vector. This transformation will convert that vector into an m by 1 vector. We'll go from an n by 1. So now we'll be in m dimensions. Think about here, we started off in R3, and we ended up with a vector in R2. And in general, this is how we can think about these mappings. This is sometimes called the domain, and this is often called the codomain of that transformation. Sometimes we think about range. There is a distinction between codomain and range, but we'll leave it at that. One last way we may choose to write this is that we give this transformation some vector x, and in general it produces some vector y. And so the way we might write this in more of the function notation that we're used to is that when we take that function, call it t, and we plug in that vector x, we get the vector y. So if we think about our domain, the set of all possible vectors, and then our codomain, the set of all possible vectors we can create, then we can sort of think about this as a mapping that transformation will kind of like our black box model here. It's going to take in a vector x. There's going to be some function inside of that box, and it's going to produce some vector called y.